Hi and welcome back to CloudNets, where networks meet cloud. Today we're going to talk about optics again. No, run. I will. It's okay. I will take it today. No, I know. Let me try to do it alone. Okay, so today we're going to talk about optical modulation and some basic features of optics we, the networking guys, need to know when we talk to the optical guys. So when we talk about optics, we talk about light, and light, as we know, is a wave. What's that, Albert? Yeah, I know light is also a particle, but we're going to talk about light as a wave today, okay? So light is a wave, and as any wave, it has a wavelength, which is basically the speed of light divided by the frequency of the light. And the wavelengths in optical communication run from 800 nanometers to 1600 nanometers. And it's important to know because we need to know for an optical device which wavelength it works on. So other than wavelength, we need to put digital information on top of the wave. So how do we turn this sinus wave into bits, ones and zeros? There are different ways to do it. The most basic way is NRZ, non-return to zero, in which we take 1 as a wave and 0 as non-wave. So each symbol, the length or the period of time in which we transmit a bit, is either a sinus wave or nothing. This is NRZ, non-return to zero. There are also more sophisticated manners like PAM4, in which we also use the amplitude of the wave, the height of the sinus, in order to deliver bits. So there are 4 heights, there are 4 levels of wave, and each level describes 2 bits. So it's either 0, 0, 0, 1, 1, 0, 1, 1, and we have 4 levels and 2 bits per symbol. Again, symbol is the time in which we transmit a single wave. But when it comes to ZR and ZR+, we talk about a much more sophisticated optical system. First, we use different wavelengths. We use DWDM, dense wavelength division multiplexing, inside the module. So it's not only a single wave which transmits, it's multiple waves, and each wave uses a different wavelength because the light can travel throughout a single fiber in different wavelengths without each wavelength interfering with the other. So we get a multiplication of the data as the number of wavelengths or lambdas we put into the fiber. So this is DWDM. Another thing we do in ZR and ZR+ is use coherent optics. That means we go from PAM4 or NRZ to QAM. QAM is quadrature amplitude modulation, in which we use not only the amplitude of the wave, but also the phase. The phase is this shift from the original sinus wave. We can shift it to the left or to the right in a certain degree that is measured in degrees, 0 to 360, in which we return to the same wave. And if we put the amplitude and the phase, the angle, on a graph, and say the amplitude is the distance from the zero axis and the phase is the angle from the x-axis, we can paint or we can draw certain symbols. Each symbol represents a certain amplitude and a certain angle or phase. And in QAM 16, for instance, we put 16 dots or 16 symbols over there, and those 16 symbols represent 4 bits. So each symbol, each period of time in which we transfer a given information package transfers 4 bits, not 2 bits like in PAM4 and not a single bit like in NRZ. More than that, we use 2 polarizations. So wavelength or a light signal can go like this, or it can go like this, figure of speak. This doubles the amount of capacity we can put in a light. This is dual polarization, so we use QAM 16 DP for dual polarization, and we can transfer 8 bits per symbol. So if our symbol rate, for instance, is 50 gigasymbol per second, so that means that in QAM 16 DP we can transfer 400 gigabit per second, which is a lot for this symbol rate, and this is what's new in ZR and ZR+. So what did we have today? We talked about wavelength, we talked about frequencies, we talked about different modulation, we talked about DWDM, and basically this is it. Thank you for watching.
You should have broken it into 3 points. That would have been, much easier. Yeah.
Yeah.
I'll
All right.
explain
Okay.
it.
Next time.
Thanks.
Next
Dan.
time.
Thank you.
Thank you
Next
for
time.
watching.